can we simplify 3 divided by 5i? What would you do in this example? The best thing we could do to get rid of the complex number in the bottom is to multiply the top and the bottom of the fraction by I. So this is going to be 3i, but on the bottom, 5i squared. And 5i squared is negative 5. So this is the answer. It's negative 3 over 5 times I. So now it's in standard form. Standard form is a plus bi. In this problem, a is 0. So it's a minus 3 over 5 times I, or 0 minus 3 over 5 times I. So how can you convert this expression to standard form? Let's say if we have 4 plus 2i divided by 3i. So first, we need to get rid of the imaginary number in the bottom. So let's multiply the top and the bottom by I. So on top, it's going to be 4i plus 2i squared. On the bottom, we're going to have 3i squared. 2i squared is equal to negative 2. 3i squared is negative 3. So we're going to divide both numbers by negative 3. So negative 2 divided by negative 3 plus 4i divided by negative 3. So in standard form, that is in a plus bi form, a is positive 2 over 3. The two negative signs will cancel. B is negative 4 over 3, and then times I. So that's the answer.
Okay, we're back. We're still talking about complex numbers, and this time we're talking about complex conjugates. And I'll start this off with an example. I'm going to take two complex numbers and multiply them. In this case, I have 5 plus 2i and 5 minus 2i. And these are two complex numbers multiplied together. But each complex number has two parts to it, so we can treat this as two binomials, and we multiply it with a FOIL operation. So we do first, outer, inner, last. And watch what happens. The first, we have 5 times 5, which is 25. And then the outer, we have 5 times negative 2i, which gives me a minus 10i. And then for the inner, we have 2i times 5, which is a positive 10i. And then for the last, I have right here 2i times negative 2i, which is negative 4i squared. And don't forget that squared. Now notice that this negative 10i and the positive 10i cancel out, so we'll cross those out. And also notice that the I squared right there, remember I squared is negative 1. So I have my 25, we'll write that, 25, and then I have minus 4 times negative 1. That's the same as 25 plus 4, which is just 29. So that's my answer. I multiplied these two complex numbers together, and I got 29 for an answer. My answer is not a complex number. It's a real number. Okay, let's do this. 7 plus 3i, just another example here. 7 plus 3i times 7 minus 3i. The same thing's going to happen in this case. Let's do first, outer, inner, last. We have 49, and then I have 7 times minus 3i. That gives me minus 21i. And then for my inner terms, I have 3i times 7. That's plus 21i. And then I have 3i times negative 3i. That gives me negative 9i squared. And notice the minus 21i and the plus 21i cancel out, and I'm left with 49 minus 9 times negative 1, because my I squared here is equal to negative 1. So this is 49 plus 9, which is equal to 58. Once again, I end up with the real number as my answer. Multiply two complex numbers, and the imaginary part has gone away. It's canceled out in both cases. And that's because of the form these numbers are in. Notice I have 5 plus 2i and 5 minus 2i. And over here I had 7 plus 3i and 7 minus 3i. In each case, the two numbers that I'm multiplying are the same other than the sign of the imaginary part. If I have two complex numbers in this form, a plus bi and a minus bi, these are called complex conjugates. And when we multiply them, we always end up with a real number. Two complex conjugates multiplied together always end up with the imaginary part canceling out, and we end up with a real number. Now, complex conjugates are also useful if we want to do division with complex numbers. We've seen how to add, subtract, and multiply complex numbers, but if we want to divide two complex numbers, it turns out we need to use complex conjugates. Let's take a look at this example. Suppose I have 4 plus 3i divided by 1 minus 2i. There we have one complex number divided by another. And my goal is to get an answer and to write it in standard form. I want to write this in a plus bi form, or standard form for a complex number. So here's how I do this. I'm going to multiply the top and the bottom by the complex conjugate of the denominator. So just look at the denominator, 1 minus 2i. I'm going to multiply the top by 1 plus 2i and the bottom by 1 plus 2i. So we see this fraction that I just wrote right here. That fraction is equal to 1 because the top and the bottom are the same. So I'm just taking my original complex, my original quotient here, and multiplying it by 1. So I haven't really changed it any. You multiply anything by 1 and it's still that same thing. But because I'm using these complex conjugates like this, the result is going to be a change in the form of the number. So let's put parentheses around here just to keep it straight and recognize that we're multiplying across the top. I'm going to do a FOIL right there and a FOIL right here, because what I'm doing here is basically multiplying two fractions, this fraction times that one. And so I multiply the denominators and I multiply the numerators. So I'm going to do a FOIL twice. So let's go ahead and do that. So the top first, 4 plus 3i times 1 plus 2i. Well, we'll do first, outer, inner, last. Well, the first gives me a 4, and then the outer gives me a plus 8i, and the inner gives me, the inner right here, 3i times 1. That gives me a plus 3i, and then the last here, 3i times 2i, gives me plus 6i squared. And again, don't forget the squared. And all of that is over my denominators multiplied together. So let's do a FOIL there. 1 times 1 is 1. And then the outer 1 times 2i is just 2i. And then the inner I have minus 2i times 1. So that's minus 2i. And then the last I have minus 2i times positive 2i. That's a negative 4i squared. Now look what happened right here. When I multiply my denominators, I'm multiplying two complex conjugates, so the imaginary part ends up canceling out. So let's simplify this fraction a little bit. This is going to equal 4, and I'm going to combine the 8i and the 3i. So it's 4 plus 11i plus 6 times I squared, and the I squared, remember, is negative 1. And then on the bottom, I just have 1 minus 4 times negative 1, which is just going to be 1 plus 4. So let's work with this just a little bit more. Up top, this 6 times a negative 1 is negative 6, and that can be combined with the 4. So I have 4 minus 6. That gives me a negative 2 plus 11i. And then on the bottom, I have 1 minus negative 4, or 1 plus 4, which is just 5. So I've simplified it a lot. And let's go one more step. Let's write it like this. 2 over 5, or sorry, I need a negative 2 there. Negative 2 over 5 plus 11 over 5i. And that's our answer. And notice the form that I have it in. A plus bi. A is negative 2/5, and b is 11/5. So this is in standard form. If you leave it like this, negative 2 plus 11i over 5. That's usually considered okay too. It's pretty clear what the answer is. Most people can go from here to here in their heads if they need to. So this is usually considered acceptable. But if your teacher says to put your answer in standard form or a plus bi form, that's usually what they're looking for. And the point here is that we got there by using complex conjugates. Doing the division, we had to do it by multiplying the top and the bottom by the complex conjugate of the denominator, 4 plus 2i. The conjugate of that is 4 minus 2i. So I'm going to multiply 4 minus 2i multiplied by this fraction, which is equal to 1. So I haven't changed my number. It's still going to have the same value, still going to be the same mathematical answer. Just multiplying it by 1 hasn't changed it. But by using the complex conjugate of the denominator, I'm going to cause all the imaginary parts to cancel out of the denominator. So we're going to be doing a FOIL here. So I'll put parentheses here to remind me that I'm multiplying these binomials. And let's think about the FOIL operation. We'll do the top first, first, outer, inner, last. 3 times 4 gives me 12. And then 3 times minus 2i will give me a minus 6i. And then the inner, 5i times 4 is plus 20i. And then the last, I get 5i times negative 2i. That gives me negative 10i squared. Now the denominator. 4 times 4 is 16. And then the outer, I have 4 times minus 2i. That's minus 8i. And then I have 2i times 4. That's plus 8i. And then I have 2i times negative 2i. That's negative 4i squared. And we'll simplify this now. Let's look at the numerator. I have 12, and then I'll combine terms here. My minus 6i and plus 20i combine to give me a plus 14i. And then this is minus 10 times I squared, and the I squared, remember, is negative 1. Okay, so that'll simplify some more. But let's look at the denominator. Look down here, the minus 8i and the plus 8i cancel each other out, and we're left with 16 minus 4i squared. And again, the I squared is negative 1. So let's simplify it a little bit further. I can combine this 12 and this minus negative 10. So that's 12 plus 10. That's 22. So I have 22 plus 14i up top. And on the bottom I have 16 plus 4, or 20. And I can simplify this one step further just by dividing everything by 2. This is going to equal 11 plus 7i over 10. And if you want to put it in standard form, you could write 11 tenths plus 7 tenths I. Just split this up into 2 fractions. And again, most people would take this or this as an answer. But if you're specifically told to write your answer in standard form, you want to write it like this. This is A plus BI form. A in this case is 11 tenths, B is 7 tenths. So the point here, complex conjugates allow us to do a division problem and allow us to get all the imaginary parts out of the denominator so that we can express our final answer in standard form.